have that it's less than 1, and so this difference equation is globally asymptotically stable. Now, this is probably not the best proof of this fact, right? This is a very easy one. But it proves that the concept of this whole thing is that we can find these K's. They do exist. They might be very large, but they do exist. And so this claim that I gave a couple slides ago is a good way of going about this, because in previous works, the techniques have been kind of ad hoc. It's, here's the difference equation, how do we prove that it's stable? Okay, I'm going to try this and that, and I'll get something eventually. But this is an algorithm that we can teach the computer how to do, to conjecture these K's and then hopefully prove them and get these results. So a few things that I wanted to mention is that most of the questions that people ask right now are dealing with these difference equations that have parameters. They don't have numbers like 920s that I had in there. And they want to know, okay, what values of these parameters, specifically like maybe alpha greater than A or something, what values of these parameters guarantee this local asymptotic stability or this global asymptotic stability? Currently, our approach only deals with the cases when we have numbers in for the parameters, but it's not too far of a leap to actually go to the parameters. In fact, this easy one is quite easy to show. K equals 2 always works for any A value. All right, so what this really boils down to is showing that some rational function is less than 1, which sounds easy enough, but if we have a recurrence of order 3, and I have a specific one that's order 3 and the K value is like 5, we have a rational function in 3 variables in which the numerator is degree 42 and the denominator is degree 44. So showing that that's less than 1 is kind of a steep task. So that's really the sticking point in all of this. So what's been done so far by us is more of a semi-rigorous proof, in the spirit of Dr. Z, of course, in which we kind of look on a grid of finer and finer grain and say, okay, well, none of the grid points have these values, but the value of the function greater than 1, so sure, it's going to be less than 1. And all of this, of course, is done using Maple because it's Dr. Z and because it's very helpful. So I have mountains of code on my website if anybody wants to check it out. To conjecture these K values and to go through a lot of different parameters. Our technique right now is to look at one of these, check a whole bunch of parameters and say, okay, well, K is 5 for most of them, so let's try K equals 5 for the general case. And this is all based on these 2 books by Jerry Lattice and different co-authors, which are basically, here's a list of all of the order 3 difference equations and what's known about them and what's not known, what we conjecture, and it's basically just a treasure trove for grad students looking for a PhD thesis. So, here we go. Happy birthday, Dr. Z. I think so.
So in your example, can you compute an asymptotic expansion?
In that example, I'm sure you probably can. It's simple enough that you probably can. I haven't done that. But there are so many, bigger difference equations that you can't.
Yes. Have you tried to develop recognition on these inequalities?
Yeah, so Christoph Kuchan told me about that, and we did try it on some of the littler ones, and it worked on the lower degree ones, but the one that I mentioned that's degree 42 and 44, it just didn't finish.
Yes.
It seems that I have kind of another present for Doron. This picture, scheme, may have application in mathematical biology. So you have to have a system that we call with 2 different time scales. For instance, if you have tricks on the gears, right? So they kind of evolving in their own way. Then winter comes, they die. The next year it goes at it. And then you're thinking of long-term behavior of this system, right? And you realize that it has nothing to do with natural dynamics. Because the second time this rotation of the Earth eventually actually dies, whatever it is. So another problem, George, is here, college drinking problem. Here you go, right? So you have college students.
Arizona State and Penn State.
Here you go. You have a class of freshmen, they're coming, there are different, actually, then they interact, right? Then the semester gone, they're gone, all starts all over. So what is here? It's this discrete map from the beginning to the end. You see? And then what's happening? After a while, it goes to a stable regime. But this stable regime has nothing to do with natural dynamics, right? Because what's happening eventually, it's oscillation, almost periodic process. It's never periodic because it's never reached this stable point, right? But it's oscillation. After a while, the system goes to initial data, it repeats itself. So you see? So this is what we have been for a couple of years. This colleague of mine, Erika Camacho, who was a student of Carlos Castillo, and my PhD student, Raquel Lopez. So we had several systems, and one of these I recognized when you tried, say, famous logistical model in mass biology and apply this procedure after a while. Then it's appear one of these recurrences, and then you have several regimes and whatever. Obviously, we never had any proof. Well, we had proof for simple models, right? But in this college drinking model, right, it's 5-dimensional system at least, abstainers, heavy drinkers, or whatever. Then it's pure computer experiment, right? But after several years, you really have oscillatory process, and this is the only way to understand what it is, because it has nothing to do with stationary points of original dynamical system. It's because of this resetting, what you're studying. Thank you.
Oh, okay. How many drunken dudes are talking?
So you should study.
Okay, let's start.
Next talk is in focus.
Can I also make an announcement? I know Arvin made it earlier about the shuttle to the hotel that's going at 7. This is not, the banquet is not going to be done by 7, but if you need to get back to the hotel, the shuttle will be at 7, and Dimex is like a show of hands. If nobody's going to be on it, they'll cancel it. Is there anybody that's going to be on the 7 o'clock shuttle back to the hotel?